Welcome back to Physics Notes. This is going to be a very brief tutorial and explanation of Newton's 3 laws of motion, which is probably what I think is a little better explanation than what's in your textbook. So the first law, if you look it up in a book or you think back to what you were taught by your previous teachers, you probably had a relatively long definition, involve objects in motion, continuing to stay in motion unless acted on by an outside force, etc., and objects at rest doing the same thing. I simplified this down to simply the first law is the law of inertia. Now, if you understand what inertia is, that should make sense. It states that inertia is real and objects will act accordingly. So inertia is the resistance to change in motion, and that doesn't mean that objects will never change their motion, but it means that forces are required for a change in motion, which is an acceleration. That's all that the law of inertia is. So if an object is sitting at rest and you're looking at it, let's say there's a box sitting on the ground. If it is at rest and nothing comes in to apply a force to the right, nothing comes in to apply a force to the left, the table applies a force upwards, the weight applies a force downwards. But if there's no net force, no force comes in that's bigger than one of the other ones and stops that interaction between weight and the normal force, this object will remain at rest. Now, one of the misconceptions that a lot of people have are what we observe on Earth. If you have the same situation, and let's say you have a table that is frictionless, it's the smoothest ice you've ever experienced, and you have a box on that table, but that box is moving with some velocity to the right, according to the law of inertia, unless there's friction or some force that would push to the left, this box will keep on moving at a constant speed. It will maintain its motion and resist changes. So that's what the law of inertia states, that objects resist changes in motion. It's the law of inertia. Now, the second law, students usually come in and their previous teachers, their middle school teachers especially, will say something to the effect of, that's the equation 1. And they will write F equals ma, and they probably used it to do some math problems or something like that and calculate a mass or calculate acceleration. I don't really like to write it like this. I think it's very incomplete. Okay? Instead, what this really means is that the sum of the forces acting on an object can be equated to the object's mass times the object's acceleration, and I'm going to draw little arrows above the F and the A to indicate that they are vectors. All right? So this is one of the most useful things that you'll use in your study of mechanics. It seems like a very simple equation, but it can get very complex. It's a differential equation because acceleration is a change. It's changing velocity over time. So we'll use that when we first start learning about differential equations. And it's something that we can graph very easily and experimentally determine masses and determine net forces acting on objects. So we'll use this a lot. Now, there's vectors involved, so we need to look at both the x and y dimension, and we'll dive into that later. Okay? Now, I also usually will think about it like this, though. Because if you write it in this form, it shows a little bit better the proportionality between acceleration and net force and acceleration and mass. So, looking at it this way, if the net force acting on an object goes up, you can see that the acceleration will go up. If there's a number here and I double it, acceleration will double. If instead I double the mass, now the acceleration will go down. It'll get cut in half. So you could say from Newton's second law that acceleration is proportional to the net force acting on an object, and acceleration is proportional to the inverse. It's inversely proportional to the mass of an object. So it's not just a formula. There's a lot of information in here, and it's something that we will apply on a regular basis. Going back to this little sideways M, if you will, that is sigma. It's a Greek letter, and it means sum. So the sum of the forces adding up, or you can think net if you want to. The net force is what's important. Now, what do I mean by that? If we go back to a little diagram, let's say I have your friendly physics teacher who is standing on the ground, right? And that's me. Hello. And we think about the forces acting on me. Well, I have weight. My weight is pulling me down. I'm going to call that weight mg. It's my mass times the acceleration due to gravity. The ground is resisting me falling through it. So the ground must be pushing back. Now, we haven't identified this force yet, but that is called the normal force, which I use the letter N to describe it. So looking at this, my question would be, would I accelerate? If you use your original definition, F equals ma, you might want to say yes, because there is a force, weight, there's also a force N. Well, the forces are there, so I must accelerate. In reality, the answer is no, because if you think about this, these are vectors, and looking at the length of that arrow and the length of that arrow, they are equal. So mg and n are both equal magnitude, but they're opposite in direction, so they'll actually cancel each other out, and the net force on me is 0. Newton's third law is very important conceptually, and that goes back to our definition of forces. Forces are interactions between two objects, and you cannot have an interaction without both objects being impacted and experiencing that interaction. So I like to think of the third law as the law of action-reaction pairs. Now, this is often stated earlier in your educational careers as for every action, there's an equal and opposite reaction. That's not 100% true. For every action, there's an equal and opposite reaction force. So I'm going to add to this the word force. We'll address misconceptions with this later, but if you think about it, if you have a person standing on a movable sled, so they're on a little box with wheels or something like that, and right next to them is another person. If this guy right here pushes on him, there will be a force in this direction acting on that student, okay? But this one will also have a change in motion because that same force acts in the opposite direction with equal magnitude on the other student. This is an example of an action-reaction force pair. Okay. Now, the trick to this is being able to identify those things. When you make free body diagrams, which is one of the first things that we'll do, before you describe a force and list a force, you should be able to describe both objects in the interaction. If you can't identify the other object, there's a strong likelihood there's not actually a force there. You should be able to identify the other object. All right, so that's Newton's 3 laws of motion. When we come back, we'll talk about some very common misconceptions about these. Thank you.